Okay, now the recording is in progress. Okay, so let me share immediately the calendar. So we see where we are. Let me make your faces small, otherwise they are in the middle and I cannot see. Okay, so today is the 25th. So we have to go through lecture 18, which is about orbits. And I think also lecture 17, which was about Newton's law and universal gravitation. Yes, these are the two that we need to cover. Monday was holiday and it was a long weekend. So I hope you had a long weekend last week. And this weekend is going to be a bit more busy because we are going to have midterm 2. So the midterm 2 is going to be between lectures on the topic of lectures 10 to 15. So chapters 3 to 5, 10 to 15. So as you see, the topic of the first part of this class, which is lecture 17 and 18, is not included in the midterm, nor the last class when we did period, frequency, circular motion. So essentially what it covers in this midterm is going to be 10 to 15. So from relative velocity, tutti kinematics. No, wait a second, lecture.
Mm-hmm. Yeah, I think that's right.
Yeah, yep. It's right.
So it starts with, it starts with relative velocity, 2D kinematics, projectile motion. So that's lectures 10 and 11.
Projectile motion. And then it goes to Newton's law, application of Newton's law. Yeah, all the elastic forces, friction, and things like this. Okay, so for today, let's start right away. What Mike is covering is Newton's law of universal gravitation, weight and surface gravity, and circular orbits. So I'm sure you have seen what he has done already in the slides, but I will go through briefly to a couple of the things here. Actually, I'm going to use probably, I can use also these slides. So we have Newton's law of universal gravitation, which is Fg is equal to capital G. So you see is different from G gravity, the small one that we have used so far. That one is the acceleration that we have been using, while this is the universal gravitational constant. And it has a specific value and is indicated with capital G. So please make sure that you remember the difference. And then is m1 times m2 divided by the distance between the two masses to the square. So the mass of each object is calculated in kilogram. The distance between the two objects is in meters. The two objects, normally they are approximated like two dots, like all the mass is on the center of gravity of the two spherical objects. And this is G. So every particle of mass exerts an attraction force on every other particle in the universe, okay? And you need to memorize this equation. This is how has been measured G, so I will not go into the details of this. What is important for you to remember is the proportionality. So the gravity, the gravitational force is proportional to the mass, directly proportional to the mass, m1 and m2, and is inversely proportional to the distance. So it's proportional to 1 over r to the square, okay? So it's an inverse square. Okay, and we will see later an exercise with this. And then the direction of the force, because this force is a vector, right? So is always along the direction that along R, that connects, where R connects the center of M1 and M2. Okay, so you see here MA, we consider MA like a dot that has all the mass of the entire object. And then we, sorry, and then we just take the distance between the two center, MA and MB, and this is considered R as R. And then the force is, of course, here is the attraction for FB on A. So B is attracting A with the force FB, which is going towards the direction of B, right? And A is attracting B with the force that is going in this direction. So here, for example, A and B, you could consider our planet and the moon. Imagine that this is MA is our planet and this is the moon. So we have a mutual attraction. And so you have the force that the moon is exerting on us and the force that our planet is exerting on the moon. And so this is always attractive. Oh, sorry. Okay, my mom, that she made a mistake, it happens. Then we can calculate and see the difference with G, the small g, okay, the acceleration of gravity. So you remember from Newton's law that F is equal to mg. M is the mass, the weight, and then we have G, which is our acceleration, is equal, this one, also to G, mass of the planet, M, small m, where M is, it could be an object at a certain distance, R between the center of our planet to M. And so we, putting these two together, we find G, that is equal to capital G, mass of the planet, divided by R to the square. And where R is the distance, as I said, from the center of the planet. And so calculating this, if we put the mass of our Earth, and then we put the radius of our Earth, we find the famous value that we always give about G, okay? So now you know the difference between the small g and the capital G, which are two different things. And of course, because you have seen that G changes, here changes, the mass stays the same, but G changes with the distance from the planet. The mass of our planet doesn't change, right? So we can have, here you see that G takes different values depending on where, or the distance above the Earth's surface. Okay, and then what is indicated here?
Veronica, Veronica,
yes.
would you mind if I added one comment about this?
Yeah, sure.
About that side. It's a common misconception that there is no gravitational acceleration anywhere above the surface of the Earth, right? And that is simply wrong. In fact, they like to say that astronauts in the space station are experiencing what they call zero gravity or microgravity, and those are all incredibly bad terms. Wouldn't you agree?
Yes.
Right. So when an astronaut is in a space station right here, you can see that the force of the gravitational acceleration they experience is almost as strong as it is on the surface of the Earth. It's just a little bit weaker. And even out where the moon is located, there is still some small gravitational acceleration due to the Earth. Right. Great, thank you.
Very good to point out that. Then also another thing that we saw from Newton's law is that an object, if there is no, remember we saw it, if there is no acceleration, the object will keep moving in the same direction and with the same velocity, right? So the inertial principle. And so here, without the force of gravity, what our object will do, it will keep moving. If the velocity is in this direction, will keep moving with this velocity and going in this direction. While with gravity, what we have an acceleration that is toward the center. And so with gravity, we have that actually is going to, the velocity is going to change constantly in direction, and will give and this is what makes this planet orbiting around. So I don't know if you want to add additional things also here, Mike.
No.
No, okay, it's good.
Thanks.
Then we saw circular orbits. So for small satellite M in circular orbit about a large body, and we call the large body with a capital M, what we are going to have is that the gravitational force is equal to the centripetal force, right? So we have G, M, capital M divided by R to the square is what is our centripetal force that we saw last couple of lectures ago.
Yeah, lecture 16, right. Yep.
Yeah, and b squared divided by r. R is the same, so we can remove one of these radius. Small mass is the same, so you see that it doesn't depend from the mass of the object. It really depends, as long as it's smaller than a capital M, it doesn't depend. And then you have the velocity, the linear velocity of the satellite orbiting at a certain distance r from our planet is the square root of G capital M divided by R. And so we can find also the period. The period is, so 2 pi R to make an entire, so the distance is 2 pi R, right? To make an entire circumference divided by the time, the period time. This, remember, is the velocity. So we have that the velocity is equal to distance divided by the time, right? So the distance here is an entire circle, 2 pi r divided by the time, which we call it also period. We've seen it the last time, is equal to the square root of gm divided by r. If we want to come out with a better description to find the period of the satellites, so we just solve this equation, and we find that the t to the square is equal to 4 pi to the square divided by G, capital M, multiplied by R to the cubes. And this is also called Kepler's third law. And this is the period of our satellites. So as you see from these two equations, when we are speaking about a satellite, the velocity of the satellite and the period, so the time that it takes to the satellite to go around our planet, do not depend on the mass of the object, but they only depend on the distance from the center of our planet, okay? So this was essentially what Mike presented in his videos. And I want to do now some problems about this. So for the gravitation, again, we said when we have two objects, M1 and M2, F1 that exerts on 2 is equal to the F2 exerted on 1, which is equal to G M1, M2 divided by R to the square. G, we have seen that is a constant, has a universal value. And so, for example, if I would ask you, which of these systems has the largest force of gravitational attraction? So imagine that here we have M1 and M2 have a certain value. You see for all these cases, A, B, C, D, E, we have different values of M1 and M2 and different radius. So here what you need to consider is what we said before, meaning that the force is proportional to M1 and M2, directly proportional, and is inversely proportional to the square of the distance. So what matters here, if we need to make some calculations, what matters is M1 times M2, which is 4, divided by R squared, 16, 1/4. This one instead is M1 multiplied by M2. Then you have additional terms. So this value is not the force. It's not the force because you need to have G. But we just want to compare them. To be able to compare them, you don't need to put G because G is in both sides. So you can just, you don't care about it. So here M1 and M2 is 1. So it's proportional to 1 and inversely proportional to 1. So this comes with the 1. Then this one, M1 times M2 is 1, while is inversely proportional to the square of R. So means 2 at the square is 4. So it's 1/4. So essentially these two are the same, these two situations. Then if I do this thing is 1 times 4 is 4, R to the square is 16. So this one is 1/4. So it's essentially the same situation over here. And then again, this one is 4 times 4, which is 16. The distance is 8. So 8 to the square is 64, that it comes to 1/4. So as you see, the biggest one, which one of these systems has the largest force of gravitational attraction, is this one. I hope it makes sense to you. If not, you can redo it considering the complete formula. Then let's see another example. So what is the acceleration due to gravity of an object at the altitude of the space shuttle orbit, which means about 400 kilometers above the Earth's surface? So in this case, what we have is that the radius is the radius of our planet plus the distance. If we look at for the distance, we have the radius of our planets plus 400 kilometers. So 6,370 kilometers, radius of our planet plus 400 kilometers. This is the distance of where the shuttle is from the center of our planet. And then the acceleration, A, we know that F is equal to A multiplied by the mass. So A is F divided by the mass. But force of gravity, we know that is G, a mass of our object, mass of our planet divided by R to the square, divided then again from the mass. So the mass and the mass goes away, the small one, which is the mass of the shuttle. And then what we have is our universal constant multiplied by the mass of our planet divided by this distance to the square. So we know the value of G, which is this one. We know the value of the mass of our planet, which is this one. We divided by the distance that we just found it before. You need to make sure when you do this that you keep the units in the same way. So for example, here is kilometer. So you need to make sure that you write it in meter because our constant is in meter. And the same here for the mass, the constant is in kilogram to the square. So you need to make sure that the mass of our planet is expressed in kilograms, okay? And then you do all the calculation and you come out with 8.70 meter per second square. Okay, so as you see here, the acceleration is lower than the acceleration that we have in the surface of our planet, right? Like the usual 9.8 that we use for our problems, meter per second square. Then another problem, the orbiting space station. Let me know, Mike, if there are things that we need to clarify from the chat.
No, there's nothing in the chat about today's lecture. Everything is questions about midterms.
Okay.
Let me emphasize that. Notice on Dr. Bindi's slides, this formula needs the distance from the center of the Earth. So whenever you're given the altitude or height above the surface of the Earth, you need to add that to the radius of the Earth, right?
Yes.
So you'll notice on the previous slide.
Yes, let me go
Right.
back to the,
Yeah.
oh,
So I
sorry.
just want to re-emphasize that. I know Dr. Bindi said that already, but that is the most common
Yes.
error that students make in this type of problem. Thanks.
Yes. Yes, so we said we need to consider like all the masses in the center, one dot at the center. And so, yeah, you need to know, you need to write it down, the radius of our planet, the mass of our planet, because that could be useful, right? And so here, every time there is an altitude, you need to consider that plus the radius of our planet. So for example, also in this problem, you are trying to view the International Space Station, which travels in a roughly circular orbit around the Earth. If its altitude is 385 kilometers above the Earth's surface, how long do you have to wait between sightings? So I hope I pronunciate this word in the right way. Sightings. It's complicated.
Yeah, that's right. And this is just a fancy way for the problem to ask, how long does it take to complete one orbit?
Yes. I wish they could have said that.
Right.
So anyway, so what we have to do is 2 pi r, right? Our circumference is equal to the velocity multiplied by the time. The time we know that in this case is the period t. So we have that our velocity is also equal to 2 pi r divided by t. This is just to remember what we are dealing with. And then we have the force of gravity, which is g, mass of our planet, multiplied by the mass of the International Space Station, which we don't know, is not given here, but we know that it'll go away at some point. R to the square is equal to what? To our centripetal force. So gravity force equal to centripetal force. They are all very similar, these problems. And so here we have a small m multiplied by the acceleration, centripetal acceleration, which is v squared divided by r. So if I can remove the mass of the object already because it's here, it's here, so I don't care about it. So it's g m r, and I can remove one of the radius because it's here, and here we have r squared. So g m e r, and here essentially what I have v squared, where v squared is 2 pi r squared divided by t squared. So from this I can find t, which is so I just move around the terms here to be able to find t, and is the square root of 4 pi to the square divided by g, mass of our planet, multiplied by the distance to the cube. So we just bring things outside, the 2 pi outside to make it easier. And r here, as you see, what is the distance? The distance is not 385 kilometers. The distance is radius of our planet plus h to the cube, okay? So this is the distance. Then we substitute all the numbers, again, making sure is in kilometers. Yes, they are all in kilometers. And then, because here I have meter square, this number will need to be in meters, okay? So you need to make sure about that, while the mass of our planet is in kilogram and this is in kilogram. But you see that here, if you want it to be precise, this one, we need to transfer it to meters, and then you can do all the calculation properly, okay? And so what we found is this value in seconds, and you can even transform it in minutes if the problem requires you to write it in minutes. Okay, so again, so these problems are all very standard. So sometimes you have something like, which one is to take into account the fact that it's proportional, directly proportional to the masses and inversely proportional to the square of the distance. Then another thing that you need to take into account is this distance, which is always from the center of our planets. Then another thing that you need to take into account are the units. Please pay attention to the units. And then you have always force of gravity, which is equal to our centripetal force. So written in this case. So they are all very, very similar. And the period, which is something that you know that is 2 pi r is equal to v times t. Okay. So
could I just add before you,
yeah.
This expression right here is better known as Kepler's third law.
Yes.
So although, you know, on the syllabus, we said we're eliminating Kepler's laws, right? We're not going to talk about Kepler's first law and second law. However, this actual result right here is better known as Kepler's third law. And this you still need to be able to know and use.
Yes, very good. Then say that in the spare time that we have, we are going to do some problems as a preparation of the midterm. So let's see. For example, here we have a force exerted by a stretched rubber band produces an acceleration of 5 meters per second square on an ice cream cartoon of a mass of 1 kilogram. When a force extended by an identical rubber band stretched the same amount is applied to the cartoon of an ice cream of mass m2, it produces an acceleration of 11 meters per second square. What is the mass of the second cartoon? So here, in the reality, is simply about, you can find this simply by applying the first two laws, so that you have the first law, actually, F is equal to M1 A1, right? This is the force. And then you know that you have a second force, which is exactly the same, because when a force exerted by an identical rubber band stretched the same amount is applied to the cartoon of an ice cream of mass f2, it produces an acceleration on 11 meters per second square. So here you're going to have that the force.
The assumption here is that the force is the same in both cases.
Yes.
The force. Great, thanks.
The force is the same because the rubber band is the same. So in one case, you have one mass and within a certain acceleration, so you have a certain mass that produces a certain acceleration. And then he said, if I apply the same force and he produces this acceleration, how much is the mass in this case? So what we have is M1 A1 must be equal to M2 A2. So M2 is equal to what? M1 A1 divided by A2. So M1 is 1 kilogram. A1 is 5 meters per second square and divided by 11 meters per second square. The units are all good, so I don't need to do any modification. I just do the calculations and I found that the mass is 0.45 kilogram. Meter per second square, indeed, because it's above and below, I can just get rid of that. And so what I have left is only kilograms. So the units are good. Then what is the magnitude of the force applied by the rubber band? So is asking actually the force. And here, because they are the same, you can use M1 and A1, but you can also use M2 times A2. It doesn't really matter. Here, because M1, AA1 is provided, it's always better to use what is provided rather than what you just find out, because if you made a mistake, then you made a mistake here, and then you are going to make an error also in the second part of the problem, right? So because those values are provided, it's always better to use the provided values. So F is equal to M1 A1. multiplied by A1. So 1 kilogram, 5 meter per second square, which is 5 Newton. And we know that the units are good because Newton is kilogram meter divided by second square. Very good. Any questions on this? If not, I think we're pretty good. Good. So now we have another example. Here we have 3 people, Mo, Larry, and Curly, that push on a 72 kilogram boat, each exerting a 80.5 Newton force parallel to the dock. And you see them here. So what is the acceleration of the boat if they all push in the same direction? And what is the acceleration if Mo pushes in the opposite direction from Larry and Curly as shown? So here in A, they are all pushing the same direction. So again, we have to consider which one is the plus X direction, this one. So they are all positive forces. Very good. So the force in the first case is with the Mo plus the force exerted by Larry plus the force exerted by Curly. So we have 3 times 80.5 Newton, which brings to 241.5 Newton. Is asking for the force? No, he's asking for the acceleration of the boat. So the acceleration is force divided by the mass. Force is equal to 241.5 Newton. Mass is 752 kilograms of the boat. So like this, I can find the acceleration, which is 0.321 Newton divided by kilogram. Now we know that Newton is kilogram mass multiplied by meter per second square. And so we can remove kilogram and we just end up with 0.321 meter per second square. Okay, so this was the answer to the first part A. Part B says, what is the acceleration if Mo pushes in the opposite direction from Larry and Curly as shown? So here we have Mo in this direction, and then we have Larry and Curly going in the opposite direction. So what we have is F2, we have that Mo, the first part is still positive because it's going in the plus X direction, but this time Larry and Curly are pushing in the opposite direction, so minus FL minus FC. Okay, so if we do the calculation, 80.5 and 80.5 goes away, so we just have minus 80.5 Newton. This is our force in the second question, in the second problem, part of the problem. So the acceleration is F divided by the mass, so minus 80.5 Newton divided by the mass of our boat, which is still 752 kilograms. So we ended up with an acceleration which is minus 0.107 meter per second square. So it's important here, of course, that you keep the minus, right? So you need to look at the problem and see that Mo pushes in the opposite direction from Larry and Curly, but at first you would think that Mo is going in this direction, in the negative direction, while after you see the problem, the drawing, so you need to make sure that you see the drawing, since it says as shown, you see that in the reality, Mo is pushing in this direction and the two in the opposite direction. So here you really have to have a negative acceleration, okay? Any problem, any questions on this? And those are typical problems that you might find in the midterm. Okay, then something a bit more complicated. A string is attached to a 2 kilogram block. So you see here 2 kilogram block, then we have a spring, and then we have the train. The other hand is pulled by a motorized toy train that moves forward at 5 centimeters per second. The spring constant is 50 Newton per meter, okay? And the coefficient of static friction between the block and the surface is mu s equal to 0.6. Okay. The spring is in equilibrium at the beginning, so t equal to 0 seconds, when the train starts to move. At what time does the block start to slip? Okay, so first of all, we have learned, let's look at the drawing. We have learned that in this case, we need to do our free diagram body. So what we have is X and Y in this direction. Then we have to put all the forces. So what forces do we have? We have the normal force that is going up, always perpendicular to the surface, the weight, which is going always down vertically because it depends on gravity, so just goes down. Then what we have the force of the spring here, and then we have the friction going in the opposite direction. So the sum of the net force along X is the force of the spring plus the force of the friction, right? Are only these two. Now, the force of the spring is positive because it's going in this direction, minus the force of the spring, which is going in the opposite direction. So this one is equal to 0. Why is equal to 0? Because when it starts to slip, means the steel is not moving, and we have static friction here. So this one is equal to MA, where A is equal to 0. So as we know, the friction is equal to the coefficient of static friction multiplied by the normal force. Now, if I write the equations along Y, I have that the net force along Y is equal to the normal force minus the weight equal to 0, right? So we have that the normal force is equal to the weight, so is equal to mg. So what I have is that the mu s multiplied by mg. Then this has to be equal, because remember from this equation, the force of the spring is equal to the friction. So this has to be equal to the force of the spring, which is K delta X. And Mike, can you write the net force along Y? Because it was not written here, so they can see it.
Yeah, let me do that.
You have a second.
I can
like
squeeze
this,
it in. Yeah, I think I can squeeze it in over here.
Yeah.
In the right-hand side of the 0.
Is equal to 0. And so you can put, yeah, normal force equal to 0. So we have the normal force is equal to, yeah, mg. So you understand why the friction here is equal to mu s mg.
Yeah.
Okay, very good. So here is equal to K delta X. So delta X is equal to mu S mg divided by K. Now, mu S was provided by the problem. It was 0.60, remember, 0.60. And then we have the mass of the block, which is 2 kilograms. Then we have G, which is 9.8. Oh, this is 9 divided by 80, but it's a mistake. This is 9.8, yes, meter per second square. And then K, is 50 Newton per meter. 50 Newton per meter. Okay, so if I do all this calculation, I came out with delta X equal to 0.235 meter, which means 23.5 centimeter. Was it asking for delta X? No, it was asking for the time that it takes. And so is delta X divided by the velocity. And so here you have 23.5 centimeter divided by the velocity, that is 5 centimeter per second, comes up with 4.7 seconds. So this one is, more, as I said, is more complicated, but at least you have seen a more complicated example, right? It's not going to be as the problems that you have in the midterm, right, Mike? So it's a bit more complicated, but
yeah, what keeps this one simpler is that all of the forces are just along the X direction or just along the Y direction.
yes.
So any vector decomposition here happens very quickly. So I'd say this is probably the maximum complexity of midterm questions right here.
Yes. Yes. Okay. So we still have 15 minutes. I don't know if you want me to present the last problem. Remember the one we said that it was a bit too difficult, or if I can find quickly maybe another problem, because I just realized I could have given a problem in the wait 1 second there. Let me see if I can find it. Allora. Okay. So maybe let me share another thing. Just to make something different, because remember, Mike, then I had the problem that it was a bit complicated. What about this one? Could it be
Great.
something
Yeah. So this
useful?
is from lecture 11, projectile motion. Yes.
Yes.
So sure, this would be a good review.
Yes. So for example, here we have chipping from the rock. A golfer sends the ball over a 3-meter high tree that is 40 meters away. Okay, so here we have the golfer, boom, kick the ball. And the ball goes over a 3-meter high tree that is 40 meters away. Okay, the ball lands on the green at the same level from which it was struck after traveling an horizontal distance of 17.8 meters. Okay, so from here to here is 17.8 meters. If the ball left the club at 45 degrees above the horizontal, so 54 degrees above the horizontal is this one, okay? This is the horizontal, this is 54. And landed 2.24 seconds later, so means that the time from here to here is 2.24 seconds later. What is its initial speed, V0? And then how high was the ball when it passed over the tree? Okay, so the first question is, what was its initial speed, V0? So Vx, we know that is the distance divided by t, right? So V along x. And V along x, distance divided by t. Do I know everything? Yes, I do, because I know that the distance is 17.8 meter. The horizontal distance is 17.8 meter. Then I also know that the time from when the ball gets kicked and the time that it gets to the ground again is 2.24 seconds later. Okay, so I can find that Vx is equal to 7.95 meter per second. Now, this one is V along x. Now, the initial velocity is equal to Vx divided by cos theta, because we know that Vx is equal to V naught cos theta. Mike, are you able to indicate here? Thank you so much. Theta is our 54. Yes. Very cool. Yes. So Vx divided by cos theta is equal to 7.95 meter per second divided by the cosinus of 50 degree, which gives you 13.5 meter per second. Okay.
Good. Yep. Yeah.
Yeah.
So yeah, I think everyone's familiar with x component of any vector is equal to the magnitude of the whole vector times cosine of the direction of the vector.
Yes.
So that gives you this. So then therefore the magnitude is equal to the x component divided by cosine.
Yes. Then we have how high was the ball when it passes over the tree. So we have the T1. We can find T1 as the time where the ball pass over the tree is equal to x divided by Vx. So the tree is 14 meters away. So x in this case is the tree, which is 14 meters away, divided by Vx, which is what I just found, 7.95 meters per second, gives you that the time is 1.76 seconds. So now how high was the ball means that I'm looking for here for y, okay, the y displacement. So y is equal to y naught plus vy t1 minus 1/2 gt1 square. So what we have here, y naught is 0 because it gets kicked from the ground. Then we have vy t1, which is v naught sinus of theta multiplied by t1, which is the components of v in this along y, minus 1/2 gt1 square. And I know everything. V naught, I just found it before. Sinus of 54 degrees is the sinus of theta. T1, I just found it before, 1.76 seconds, minus 1/2 m gt square. So this is g and this is t square, and it gives you 4.03 meter.
Oh, it looks like our time is up.
Yes. So I have another problem here, and I can put it in the slides and you can see the solution just in case if you want to do some extra problems to get ready, so I can also put these problems on the slide and upload them in the Zoom and upload the slides too. Okay, so yeah, go back to study. And so the midterm 2 is going to be similar to, the style is going to be the same as the midterm 1. So we are going to have multiple questions that you are going to with multiple choice answer. And we are going to have some answer that you have to fill in the number, like it was in midterm 1.
Could I just remind everyone that RLAs are going to continue to be at this Zoom address from now until 1:30 p.m. So if you have questions on your Mastering Physics homework or anything else, feel free to come back.
Okay.
Thank you.